Tunable degenerate optical parametric oscillation with coupled microresonators.
Thank you. Well, good afternoon, everyone. So today I will be presenting this work that was a good collaboration with a few other members of our group. So to start, we are using an integrated photonics platform. We are using waveguides of silicon nitride. And this is a nice platform for what we want to study, that are nonlinear optical phenomena, because it has a good, high index of refraction. It means we can have a good confinement of light, but also we can have relatively long interaction lengths. With that, we can achieve very nice nonlinear phenomena. Okay, we can have, even in small nanofabricated chips, we can have interaction lengths of about 1 meter. That's a lot to have a fiber rolled up there. This is also a broadband device. On the other side, we have optical cavities that are similar to these waveguides, but they are wrapped around. They have this confinement of light, but besides the spatial confinement of light, it can have also temporal confinement of light, and with that we can achieve very high intensity levels inside the cavity. We can achieve nonlinear optical effects even with about 1 milliwatts of input power. This is about the power of common laser pointers, right? And in this kind of case, we can have this interference, this constructive interference, if we have the wavelength of light, or the size of the cavity is a multiple of the wavelength of light. And in these particular cases, we have we can achieve this intensity. So this has been used for several effects and several applications of nonlinear effects of light. One of them is the formation of frequency cones, for example, that's been highly used, highly explored. And in this case, we have input CW laser, and the output has multiple frequencies. There are one frequency for each FSR, or each mode of the cavity. And in the case of silicon nitride, that is what we are interested here, the nonlinear effect is a third order nonlinear effect, because silicon nitride has inversion symmetry. We do not have even order nonlinearities, where two photons of the pump laser are annihilated to a creation of a signal and either pair. Okay, and of course we need conservation of momentum and energy to achieve that. So in the end, we have a dynamic equilibrium between optical nonlinearities, or the chi3 of the material, and also the dispersion of our device, of our setup. So we can see the role of dispersion as, if we had a dispersion-free cavity, we would have modes equally spaced. But in the end, in practice, due to material properties or even geometric properties, we have dispersion. The modes, they deviate from this equally spaced grid. Okay, we can have normal dispersion where the distance decreases with increased frequency, or the opposite. And we can describe the position of these modes with respect of a reference mode here as this exponential, this sum, where the first term represents the FSR, the distance of the equally spaced grid, and the second term here is the group velocity dispersion that represents this deviation. And we can measure that. Okay, so we are interested in an effect called the optical parametric oscillation that can be achieved in, for example, chi2 or chi3 media. In chi2 media, we are dealing with parametric down conversion, where one photon is annihilated, one pump photon is annihilated to create degenerate idler and pairs, idler and signal pair, and they are degenerated in frequencies. But we are interested in Chi-3 effect, where we have two pumps, and each photon of these pumps are annihilated for the creation of the degenerated pair. Okay? And this, we are interested in this effect because it has very nice properties. For example, this is a process where we have a threshold. The threshold is where the losses are exceeded by the gain capture. So this process, this frequency here starts to oscillate. When we are below the threshold, we have a squeezing of the vacuum. And when we are above threshold, we are oscillating on only two possible phase states. They can oscillate in phase with our pumps or pi out of phase with our pumps. Okay, this is why we have a phase-sensitive amplification that happens every pi. And this binary phase state can be explored for several applications, right? Since we have only two phase states that are possible, and they are the complete opposite of each other, they have been used for optimizing complex problems like simulating Ising machines with photonic processors. They can be explored for true random number generation, and they can also be, when we are working below thresholds, we can have the generation of squeezed states of light. And all these properties, they explore one very particular phase of these binary phase states, is that they are equally probable that they have due to quantum fluctuations of the vacuum. So this is a true, oops, okay, I think we run out of battery. Here. So we have a true random phase, okay? All right, so in Chi-2 media, the DOPO, the degenerated OPO, has been implemented in free space setups for that photonic Ising machines I have shown you, but also in integrated platforms. But despite in integrated platforms, we have controllability and reproducibility and scalability mainly, but we have the signal and either pair are 1 octave away from our pump. So for that, it's necessary to have a control of dispersion of these cavities for this full octave, right? A huge spectral bandwidth. But we are interested here in Chi-3 OPOs, and with that, we have a much simpler solution for dealing with dispersion, because we can have two pumps that are spectrally close, and the oscillation will happen at a central frequency. So we have a much narrower region to control dispersion. But on the other hand, the phase matching conditions for this OPO, this DOPO phenomena to occur, also provides phase matching for several other phenomena, as for example the generation of frequency cones. Several other modes start to oscillate, and this can be a problem for us, because first it's taking energy away from our desired signal. And second, it can provide instability or complex dynamics of our system. Okay? So what we propose here is a way to deal with all these complications, that we want to suppress these non-degenerated forward mixing signals that populate other modes. We want dynamical, on-the-fly DVD control, so we do not have to have several devices fabricated and see which one works. We can control on the fly. And we also need phase-locked pumps, because as I said, we need the oscillation happens in phase or pi out of phase with our pumps. So we don't need complex locking schemes between lasers to have that in our devices. So what we propose is the use of coupled resonators or photonic molecules. And if we have coupled resonators, we have a frequency splitting here that depends on the strength of this coupling. But here we only have two modes, and we need 3 modes for our 4-wave mixing. So we propose the use of 3 coupled resonators, and we can see here that when we are in the degenerate case, we have 3 equally distant modes, but we can change for different regions where we have one mode closer to the other. So we have this device fabricated and looks like this. So we have here 3 rings. We also have electrical contacts, so we can control the position of these modes. And since we have 3 coupled resonators, the hybridization here results in 3 modes at each FSR of our cavity. Okay, so this is an experimental result of our the transmission of our devices. So at each FSR we have 1 mode here. And we are going to explore these 3 modes for our mixing process. So what I want to show here is first the GVD control of our setups. So when you talk about group velocity dispersion, we can take one of these modes, for example, the red mode here, and with respect to one reference frequency, we can calculate the spectral distance from each mode to that reference, and with that we can show that our devices are in the normal GVD regime. That is what we expected, we fabricated for that. But if we look not for different modes here, different order, but if we look for only for a single triplet here, we can change the relative position of these 3 modes. And we do that with integrated microheaters on top of each ring. So as we apply current for one of these heaters here, I show that, for example, here we have this mode is further away from the central as this one, and on top here we have the complete opposite. So we have dynamic control of these distances here. And with a stimulated forward mixing phenomena, we can show that, for example, near the 0 dispersion, we have higher conversion efficiency as compared to when we are far from the equally distance situation. Well, let's look back for the dopo here. So as I said, we needed coherent pumps, and for that we generate 2 different pumps from a single laser using electro-optical modulator. We generate 3 sidebands, 2 of them are in resonances with our modes, and 1 of them is out of resonance, not taking part of the experiment. And what we do is detune these 2 pumps with respect to our cavity or triplet, and this is the realization of one experiment here. So what we are seeing here, this big line, these white yellow lines here, are the pumps, and when we approach the 0 detuning, we can see the oscillation in the central frequency. Okay? I always say that when I present this slide, I need to play this GIF a few times here because it was too much time in the lab to get this result. I like to look at it for a few times here. So, what I show here is a realization of this experiment, and what we have is about 17 dB of contrast between our pumps and our oscillation signal. In terms of conversion efficiency, it's comparable to other experiments, but we have all these advantages as I've been discussing so far. But with that, I show how we can optimize this signal. Okay, so we have here the orange curve is when we have 0 dispersion. So the 3 modes involved are equally spaced. And we have this orange curve here, the amplitude of dot oscillation is smaller. But when we go to the normal dispersion, where this distance is smaller than this distance here, we can achieve a much higher intensity of the central frequency, this nonlinear frequency here. And this is because, as we started discussing the balance of nonlinearity and dispersion, we have self-phase modulation effects and cross-phase modulation effects. In this case, the effect of cross-phase modulation is bigger than the self-phase modulation. And the 2 modes here, they experience cross-phase modulation and due to the other pump, and self-modulation due to themselves. But the central frequency will experience 2 times the cross-phase modulation because we have 2 pumps, and the self-phase effect is very small. So this the central mode will be redshifted more than the two pumped nodes. So this is why we have to start with normal dispersion, so we can compensate for that. Okay, so we have recently published this on ACS Photonics, this work, and what I have shown here that we have a device that we can control and dynamic control the group velocity dispersion. We can have phase-locked dual pump scheme, very simple, and we can produce these devices. But not everything is, as I said, we have faced several issues, and I recommend you guys to see the Luca poster that is going to discuss this in more details and dynamics where we are studying, and also Luis' poster where we are exploring below threshold application of these setups. With that, thank you very much.
Thanks a lot. Time for a few questions.
Thank you very much for the nice talk. Nice device, by the way.
Thanks.
And I was curious about on slide 6.
Okay.
You mentioned about squeezed states.
Yes.
I was just curious about what are these and how to achieve them. Could you please comment a little bit about this, please?
What are squeezed states in general?
Yes.
Yeah.
What are these states and how to achieve this?
Yeah. So we have natural noise when we have this diagram here. We have amplitude and phase typically, and we cannot, with infinite precision, define both of them simultaneously. So in general, what we have here is a circle that we have uncertainty. Due to the principle of uncertainty, we have uncertainty in these two cases. But when we have a squeezed state, we can reduce the noise in one of the quadratures, and this results in the increased noise in the other one. So instead of having a circle here that represents the light state, we have these ellipses here. We still obey the uncertainty principle, but in one of these quadratures we are below this typical minimum noise. So in this case here, we can achieve that if we are pumping near the threshold, a little bit below or above. We can have this state where we have squeezing the phase noise, for example. So yeah, in this device we can achieve that, and well, we are starting to explore this. Is what's the road.
Okay, quick question.
I was curious about the measurement process. Which kind of signals do you send? Which kind of signals do you receive?
For the squeezed state or for the...
For the measurement of the resonators, the couple resonators.
Yeah, so we have, for the measurement we have one single laser, and then we use an electro-optical modulator to produce sidebands. So we actually have 3 pumps that have the same intensity. Okay, 2 of them we are in resonance. In the ideal case, we are in resonance with the cavity modes, and one of them doesn't take part. It's not part of our experiment. And what we have here is while we detune these 2 pumps, we are moving, and in the 0 they are in complete resonance. So we have optical spectrum analyzer to have this kind of plot, but we are also filtering only the central frequency to study the temporal dynamics of this nonlinear signal here. And we want to send the pumps away and use only this for our applications. Not sure if I was enough, but
Can you go back to 14, this slide 14?
maybe
Yeah.
here.
Yeah, it could be one for the one you showed. Yeah, this one.
Okay.
So I was in doubt of how the measurements you show are applying in this image. like those lines are the guidelines. You send the pulses, and your resonators are in between, and micrometers, which type of signal you apply to them. And
Okay, so we have the optical modes here. Light is in all the 3 rings. Okay, so when we are in this case here, for example, when we send light into our device with this wavelength, we have, for example, this case here. So we have light in the 3 rings, but the central ring is out of phase with the external rings here. And if shifted to this wavelength, we have this case here. And for the red one, we have this kind of here. So we have these modes of our cavities. And for the nonlinear signal, we send 2 pumps, one aligned to the blue resonance, one aligned to the red resonance. And then we see the generation of light in this central resonance here. For the microheaters, we pass a current, DC current, just to heat the setup and change the refractive index. And that's it. We can control these positions by controlling this refractive index of our rings here. Okay, not sure if I answered you now, but we can discuss further.
Okay, thanks a lot. Let's
Thank you.
move to the next speaker.
Ah, entendi. Obrigado. Obrigado.
Okay, our next speaker is Lucas Squillante from Rio Claro, from Unesp, and he's going to talk about the Grüneisen parameter as an entanglement compass and the breakdown of the Hellmann-Feynman theorem.
Thank you very much. Good afternoon, everybody. I'm Lucas, and I'm a postdoc at the research group of Professor Mariano de Souza at the São Paulo State University in Rio Claro. And I'm going to talk about the Grüneisen parameter and its relation with quantum computing. And as a side result of this paper, we have the breakdown of the Hellmann-Feynman theorem that I'm going to talk a little bit about. First, the outline of my presentation. I'm going to talk about the motivation and goal, the critical point in the Grüneisen parameter, why it's important in the sense of critical phenomena, and its relation with quantum computing and entanglement. And then I will finish my presentation with some outlooks and conclusions. First of all, this is our lab in Rio Claro. We have a Teslatron PT cryostat. We are able to achieve temperatures of 1.4 Kelvin up to 300 Kelvin. We can apply magnetic fields up to 12 Tesla. So this is just to show that some of the quantities that we'll be discussing here, we measure back in Rio Claro, for example, thermal expansion. And just to remind that sometimes you can say in nature that let's imagine an infinite system, but in the lab we always deal with finite systems. So this is the motivation for this slide. Of course, the motivation to talk about quantum computing is that we have all been searching for a way to perform quantum computing in an improved way. So we have seen a couple of weeks ago the Majorana 1 has been released. So everyone is going like in a gold rush to achieve the best way to make quantum computation. And we also have the quantum computer. There are entanglement-based systems, and this is the one I will be focusing on this presentation, because the Majorana 1 operates in a different mechanism. So, before talking about quantum computing at all, I'm going to make a brief review of the Grüneisen parameter. The Grüneisen parameter is a thermodynamic parameter that encodes the ratio between the thermal expansion, how much a system increase or decrease its volume when you give temperature or decrease temperature, as a function of the specific heat. So why is this parameter important? First, because you have a connection between thermal expansion and specific heat. This is a fundamental aspect of this. but more importantly because the Grüneisen parameter encodes the entropy variation with respect to pressure, for instance. It can be other things like electric field, a magnetic field, or other things like that. And the entropy with respect to the temperature. So it weights where your entropy is going to increase or decrease. So this is very important when you're looking at critical phenomena, like where is the critical point? What happens near the critical point? Because at the critical point we have an entropy accumulation because of the competition between phases, and this gives rise to a signature in the Grüneisen parameter. So the Grüneisen parameter is a good tool to explore critical points, and also phase transitions, of course. We can extend the concept of the Grüneisen parameter to quantum critical points, but there's a problem, because a genuine quantum critical point lies at t equals 0. So what happens to this Grüneisen parameter exactly at 0k? The entropy goes to 0 as a result of the third law of thermodynamics. So does the thermal expansion in specific heat. So this guy here works fine in the vicinity of quantum critical points, but does not work right at a genuine quantum critical point. So what we did was to propose a distinct Grüneisen parameter that works well on a 0 Kelvin. But before talking about this definition, I will discuss the simplest toy model to describe a quantum phase transition or quantum critical point. This is, I think you all know this is the easy model, but more specifically, this is the one-dimensional easy model, the quantum version of it with a transverse magnetic field. So let's assume the ground state is spins pointing in the up direction, and there's a magnetic field in the transverse direction. So what happens in this model is that when you increase magnetic field and it equals the J, the coupling constant between adjacent spins, what happens is that you change the ground state from a superposition between up and down states to a quantum paramagnetic. So in other words, you flip the spins, and this is the simplest model to describe a quantum phase transition. Okay, so this is exactly the quantum critical point when the magnetic field equals the coupling constant. So what we did was to propose, as I mentioned, a new definition for the Grüneisen parameter that works at exactly 0 Kelvin. So the Grüneisen ratio, the Grüneisen parameter, it can be defined as the Grüneisen ratio, but it incorporates the variations of the free energy of both a temperature and a tuning parameter. As I mentioned, it could be a lot of things. But what happened is that we proposed a quantum version, we named it gamma 0k, that instead of the free energy, we're now dealing with the ground state energy. And instead of temperature and another parameter, we are dealing with two parameters or two energy scales. So imagine you have a quantum system that you have two energy scales competing, or in the case of the easy model, you have the magnetic field applied, and then you have the exchange coupling constant. So these are competing energy interactions. So the Grüneisen parameter at 0k, instead of quantifying the thermodynamic entropy, it now quantifies, in this particular case, the global entropy, or the global entanglement entropy. So now we can think that the thermodynamic entropy is 0 at t equals 0, but the von Neumann entropy is not 0, because you have a pure state, so to say, at t equals 0 Kelvin. So what we did was we make this proposal of this parameter, and we also made an alternative approach to compute global entanglement. You can understand global entanglement as you can have single site entanglement, how one spin is entanglement to the others, and you can have global entanglement, how every spin is correlated with one another. And this, of course, is very important for entanglement-based quantum computers, because you rely on entanglement. So if they are more entangled, it's good for quantum computation, because you have the resilience for noise and all other stuff that can affect your quantum computation. So based on this proposal, what we did was to apply this to the easy model, and what we get was a signature right at the critical point. More specifically, we have a divergence of this parameter right at the critical point. This indicates that the von Neumann, the global entanglement, is infinitely varied when you vary a tuning parameter like magnetic field. So this shows that if you have a quantum system and you are interested in making quantum computations, your entanglement entropy will be maximized, or the entanglement entropy variation will be maximized close to critical points. So if you're looking to optimize your entanglement-based quantum computation, go to close to the quantum critical point, because your entanglement will vary a lot in that region. And also, as we propose another way to compute global entanglement, we have tackled into the Hellmann-Feynman theorem, which is usually which was proposed by Feynman and Hellmann to study molecular forces in many scenarios. But this, you can see that we have here an open circle, because this is a divergence. But here, since we are connecting the global entanglement with the first derivative, the minus sign of the ground state energy in a turning parameter, this breaks down. So we have shown that at this particular point, the Hellmann-Feynman theory breaks down. This is an important theorem for quantum mechanics, and also that entanglement is varied a lot close to quantum critical points. But as I mentioned before, we can have divergences in nature. When you make a calculation, oh, it diverges, it goes to infinity. But do we have infinities really in nature? Can we measure at the lab an infinity quantity? And based on that, as a step further, we have used the so-called non-extensive statistical mechanics. Maybe you guys know the Constantino Tsales from CBPF. He proposed a new form of entropy that works well where the Boltzmann-Gibbs entropy fails. And the Boltzmann-Gibbs entropy fails right at the critical point. There's a whole justification for that, but what we did was to correct this divergence, not only for this particular problem, but we have used the fact that right at the critical point, every critical point, either classical or quantum, we have a breakdown of the extensivity character of the entropy. The entropy does not scale more of the system size. Actually, at the critical point, the thermodynamic entropy scales with the logarithmic of n of the system size. So we break down the whole thermodynamics. And how to fix that? We propose to fix this with the non-extensive statistical mechanics, and based on this, we have removed the infinity. So we have focused on this open circle to make this a full circle. So this is not a divergence anymore. Instead, we show that for the correct value of a particular parameter Q, the divergence goes away. So we have regularized, in terms of the non-extensive statistical mechanics, the critical phenomena theory that some of you guys may know that it predicts singularities right at the critical point. So based on this work from 2023, we have proposed this new type of Grüneisen parameter that it can be served as an entanglement compass. So if you want to know where your system is more entangled, you can use this parameter to quantify in which conditions entanglement is maximized. And also, this entanglement variation is enhanced close to quantum critical points or critical points, and that you can use this to construct more reliable or more optimized quantum computers based on this. And that we have removed this infinity from this because, as I mentioned, in the real world, we don't have infinity. We have finite quantities. So with this, I thank you very much for your attention. I thank the organizers, and thank you very much for your attention.
Thank you very much. We are well on advance, well on time, so we have time for questions.
So can you just give like a picture of what is this new Grüneisen that you guys? It is still like relate to the thermodynamic quantities. Can we still like relate to that?
Yes, we can.
That's something that.
We can, because it has the similar structure from the one from the thermodynamics. So if we get like thermal expansion, you can write thermal expansion like the second derivative of free energy with respect to temperature and, for instance, the volume. In the specific heat, second derivative. And here we have that the free energy corresponds to the ground state energy, and temperature and other tuning parameters correspond to two distinct tuning parameters or two energy scales. So if you have two competing energy scales in your system, you can use this to quantify where entanglement is maximized in your system.
Thank you for the... Yes? Okay. So thank you for the talk. So I'm not from the field, but I want to understand why you want to have the variation of the entanglement to be maximum or very big to make a good quantum computer.
Sure.
I was wondering, you wanted it to be maximum? But
what is the advantage?
Yeah.
Yes, of course. If we are interested in particular conditions where entanglement is maximized, so all the spins are more entanglement, for instance, this means that in particular conditions, the resilience of your spins or they will be less susceptible to external noise because they're more entangled. It's like they are fighting with each other to stay entangled. So there are a lot of works in the literature that relates that if your systems are more entangled, your quantum computation goes faster and it's more optimized, and then you have this resilience to external noise too. So this is to optimize structures of quantum computing that already exist. So if you are looking to use a system, for example, a Joseph junction, there was a guy here, yes, Joseph junctions. These Joseph junctions are made of superconducting materials that can have properties like the superconductivity can be close to a quantum critical point, for example. This is very investigated in the literature, and then you can tune your system close to this region because entanglement will be maximized, and then you will perform more optimized quantum computations.
So the entanglement maximized near the critical point?
Yes.
I thought it was the variation of entanglement.
Yes, it is. But entanglement is also maximized because we have, this is the global entanglement versus lambda, where lambda is the ratio between this is for the one dimension is a model. So this is maximized because this is an open circuit. So if you calculate right at this point, this is infinity. So entanglement is infinity right at the critical point. And that's what we have been working to regularize in the other work I showed you before.
You are computing the entanglement entropy, right? So it goes like log n in that point. Am I right?
Sorry?
I mean, in that point is log n, am I right?
Yes, from the usual theory, yes. But what we did was, because what we did was to correct this.
Another question that I think is a continuation of the first one. I completely failed to understand in which limit your new parameter goes back to the original one. I understand that you say one corresponds to the other, but it looks like a moral correspondence.
I see.
Is there a precise procedure that brings this to this, so to say?
No, because this quantum version of the Grüneisen parameter only works at 0K. If you are not in 0K, then this guy plays the role. This is the correct way.
Okay, this was the second question. If you go non at 0K, this parameter and this parameter are two different things.
Yes.
I see.
So this question, this parameter arrives because my advisor came during my PhD and said, well, if the thermal expansion or all the quantities related to entropy goes to 0, what happens to this quantity at 0? It's undetermined. You cannot use this. But people have been using this to explore the vicinity of quantum critical points. Of course, we cannot achieve 0K in real life. But what if we are interested in truly investigating a genuine quantum critical point? Then we have to go to another, the Grüneisen parameter, which is this. And it has reminiscent with the thermodynamic one.
I see. So they really don't talk to each other because they are defined on different domains. So
yes, exactly. You can, we know that at finite temperatures you can have both thermodynamical entropy and von Neumann entropy, for example. that you can have this because of they are not excluding.
Right, but I would say that, for example, if you are in a thermal state, they should agree. So
Yes.
you should have ways to check that the T different than 0, these two for special states. Like, for example, for a thermal state, they do agree. For a thermal state,
No.
They don't.
No.
I see.
This is strictly for 0K. I'm just mentioning that you can have von Neumann entropy even though you're not at 0K.
Okay. Other? Okay. If not, we can. Thanks, Lucas.
Thank
again.
you.
And we can move to our third speaker, who is Pedro.
Ok. Onde é que fica vermelho? Ok. Ok. Beleza.
Okay, we have Pedro Paraguassú from PUC in Rio de Janeiro, and this talk is going to be about the effects of the quantum system upon a classical mesoscopic nanoparticle system.
So, thank you. So, what we want to study, what I mean with effects of a quantum systems, blah, 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 is just that we are interested in investigate the interaction between a quantum and a classical system. Why this? Because the classical system is more easy to measure and to deal with, so we kind of trying to see how we can use this interaction to infer the infer some information about the quantum system by measuring the classical one. This is the idea. I forgot to say, but I am a theorist working in optomechanical lab. So we are developing these techniques and investigating how things are emerging. So one thing that we know is that when a classical system interacts with a quantum one, its equation of motion will be a quantum-induced noise, so it will be a stochastic process. So we are deriving this stochastic process and see how we can obtain information from this noise. Well, one example where this appears is in this work of quantum mechanics of gravitational waves, and the idea is that if you quantize the gravitational wave and this quantized gravitational wave interacts with the arm of LIGO, this arm will obey a stochastic process that you have a noise given by this funny distribution here, is a Hadamard distribution. This is just one example, but another example, which is where I'm working, is in levitated optomechanics. As I said, I work in an optomechanical lab, but I am theorist. This is Thiago Guerrero group. This is not Thiago, this is Gabriel, one of the students. And we are trapping silica particles in vacuum and trying to reach the quantum regime for these particles. And this is where I want to see the theory and see how I can measure quantum states. So obtain any information from the quantum system by measuring the classical system. The contents of the field is that we have a particle, the silica particle has like 10-8 atoms, so it's a massive object. You do not reach the quantum regime, so you want to reach the quantum regime. There are some groups that have already reached the ground state. This is the limit of the experiment results. These are our results from our group at PUC. We expect that we reach this line here this year. So, but as I said, I am theorist. I'm a theoretical physics. So what I want to do is, suppose that we already have this quantum system. We reach the quantum systems for 10-8 atoms, this silica particle. Let's see what we can learn about this and by using this idea of quantum classical interaction. So we have this work here, quantum-induced stochastic optomechanical dynamics, where you choose 3 systems. I only talk about 2, but suppose that I have this silica particle trapped with a cavity, and this I have quantum light interacting with the classical particle, and see the movements of the classical particle to infer the state of quantum light. And I can also have the opposite. I have a quantum particle interact with classical modes of light. Suppose that we have this quantum particle. And the most interesting case, I will show why, is because you can probably measure if you work it, is have two particles, one quantum and another classical, interacting via Coulomb interaction. So the thing is, I can work all this system with the same Hamiltonian, with just two harmonic oscillator linearly coupled, and the idea is to derive a stochastic motion for the classical system that I choose to. So this will be the classical that are interacting with a quantum one. So the idea is I have the reduced density matrix for the mechanical system, we call it the mechanical system, and use the path integral formalisms to integrate over the initial state, and now we have this super propagator, which is a double path integral. I have two coordinates here, the Lagrange, usual Lagrange, but now I have this Feynman-Vernon influence functional that gives the interaction that can be written simply as this bracket equation here. So by inserting a quantum state for the quantum system that I choose, I will see the effects on my path integral. And the idea is, well, until now, all things are quantum, but just one example, I have the vacuum state, and the super propagator becomes this biggest fraction here. I have a noisy kernel that I can write. The solution allows us to write as a noisy kernel here, the usual Lagrange, and we also have a quantum dissipation. It's still quantum, but when I do the least action principle with the classical assumption that the forward and the backward, I have two coordinates in the path integral because this probability is associated to a probability, not to a wave function path integral. That's why 2. If I assume this, I will derive a quantum induced stochastic dynamics, or just the harmonic oscillator that I'm working with this fluctuation noise, this quantum origin fluctuation noise that depends on the A bar, the coupling, and you see that is a colored noise, so it depends on cosine. And I also have this dissipation that comes from this big term here that I omit for simplicity. And okay, so we can, this is just the general result for the harmonic oscillator coupled with the linear interaction. But if I have the particle interacting in the quantum light, I can integrate over the modes of the light, over the frequency, and this will change my noise. When I do this, I find like fun expressions. I have this color noise here, white Gaussian noise here, and also a double derivative of the Dirac delta. But most of these terms are very small for the parameters, realistic parameters. And in resume, we find this expression here for this noise. But there's a problem. This noise is very weak, so we cannot use this case to measure the quantum state. The environmental noise will overcome this, so this not occur. This do not work for practical purpose. It's just for curiosity. It becomes just a curiosity result. But we can have a noise that possibly measured by the classical probe. I can call that. If I have it in the squeeze state, the noise will be enhancement by the squeezing parameters, so the squeezing radius. And I also have a non-stationary noise that appears. So instead of the difference between 2 times, I have the sum of the 2 times in the correlation. And for the case of the 2 particles, one quantum and another classical, this becomes more interesting because we can possibly measure, if I assume that we can have a quantum silica particle squeezed with 30 dBs of squeezing, we can have appreciate some increase in the variance that could be measured in principle for this case. But in general, it's not too good, this true oscillator, but this is just have some potential possibility to measure, gain some information from the quantum state if it is squeezed. Another case that we find is this for the coherent state. We also, besides the noise, we also have a deterministic force, so it's becoming a driving, so the quantum system now is doing work, and this is just continuation of the work, is that, so since I have a work, if I have a coherent state, the system is stochastic, why not ask some questions about this work? Well, you know that the average of this stochastic work obeys the second law, is greater than the equilibrium free energy, and we can ask about the probability to violate the average bound. It's not a truly violation because the bound is for the mean, and we can investigate how the properties of the noise affect the stochastic thermodynamics. It's on a kind of a spin-off from this work, and you see the classical case is bounded by 50%, depends on the number of phonons in my coherent state, and it will have more probability to have these apparent violations, but the quantum case, as increase my time of interaction, the probability start to rising as I increase the time. So this is in archive right now. We sent to the referees. But okay, as I said, this is not when you first started the work. You really have some expectation to see some information for the quantum system, but it's not working. And the problem is that we have just two harmonic oscillators that is not truly quantum. So we ask ourselves, why not interact with a truly quantum system, or more the simplest one quantum system, just a qubit. So motivated by these experiments, recently we have a nanoparticle trapped with an atomic ion, and this is a old work that you have a qubit from a superconductor chip interacting with a clamped mechanical resonator. So why not to see what happens with, and I have a qubit and a classical harmonic oscillator. Well, to start this idea, we start with the James Cummings Hamiltonian, and we derive the same idea of the influence functional, but now we have this Pauli matrix. This is a work in progress. And for arbitrary quantum state in the Bloch sphere, we have this quantum induced stochastic dynamics of my harmonic oscillator. So I have a deterministic force, and I also have two noises appear doing the coupling, just to show the correlation between this noise is very messy, but we are working through. But some interesting that already appear is that the average of my position will be proportional to the driving force. That is proportional to the p-value that determines the superposition in the Bloch sphere. So in principle, we are studying this, investigating. We could infer the state of the qubit by measuring the mean of the position of the classical oscillator. This is as I said, it's a work in progress. This guy here is doing all the calculation for us. He's from CBPF. And that's all that I want to talk with you. I want to show this quantum-induced stochastic dynamic and somehow show how could be used in principle to infer quantum states. And to send the message of this line of the work, we are working in different cases and applications. We even have stochastic thermodynamics applications. And one next steps is to consider two entangled systems interacting with a classical one and see if we can have some imprint of the entanglement with the classical system. So it's a work in progress, and we are investigating, and thank you, the organizers and everyone, for listening.
Thanks, Pedro. Questions?
Hi, Pedro. Thank you very much for the nice talk. I fail to understand what is this probability related about that you mentioned in your presentation.
In the
Probability of what?
in the work distribution.
Yes, you mentioned two cases. One that the probability increases, which is associated with a possible.
Yeah, I think I was fascinated. I explain here, right? So, yeah, of course, I did not explain correctly. The idea here is that I consider just a classical case. I ignore the quantum noise. I just want to see intrinsically if the classical noise how affects the work. The same expression for the work. I want to see how this affects this probability of the apparent violations. So when I increase in time, I have some optimal times that is due the cosine dependence. Is a oscillatory work that reaches the bound of 50% and depends on the number of funnels. When I increase the funnels, I have some ranges here of time that is the probability is way less, right? But the amplitude is the same over time, or by increasing the time. So we cannot do too much. But for the quantum case, and now I ignore the environmental noise, just the quantum noise to see how you affect. The idea is kind of the same, but now when I increase the time interval of the processes of the interaction, I will have more. The probability is increasing, the amplitude is decreasing, but so the probability in a way are increasing. That's the idea. Just to compare, it's just a more I don't know. There's no practical applications in this. It's just to connect stochastic thermodynamics with this formalism.
Thank you. Other questions? Okay, if not, we can thanks Pedro again. Now we can move to the last speaker, who is Lauro. Okay, our last speaker for this session is Lauro Barreto Braz from USP, and he's gonna talk about competing magnetic states on the surface of multi-layer ABC stacked graphene. Lauro, the floor is yours.
Thank you. So I'm pleased to talk a little bit about this work on the possible competing magnetic states on the surface of multi-layer ABC stacked graphene. This work was developed in collaboration with Annika Black-Schaffer in Sweden and with Tanay Nag in India. So let's start over about the story of this material called ABC stacked graphite, or also rhombohedral graphite. So in the beginning of the 60s, there were a few proposals that another possibility of organizing graphite could be doing this kind of ABC stacking. However, it was also predicted to be thermodynamically unstable, such that an experimental realization would not be possible in nature, for example. However, with new advances in manipulating the van der Waals interactions in few layer systems, such as graphene, experimentalists now can realize this system with up to 50 layers. So, but why exactly would such a thing be interesting if not by the motivation of doing something that was predicted to be forbidden? Well, that's because this system has a local in momentum flat band. So as one increases the number of layers in the system, there is a flat band located around the K and K prime points of the Brillouin zone in the sense of graphene that increases in length in momentum space as the number of layers increases. So the goal here is to study the effects of this flat band that naturally happens in this system in the limit of many, many layers. So the main motivation is this experimental work where they measured actually competing correlated states in this system. So here what you're seeing is the density of states as measured by STM experiments. And what you see in the black curve here, where the x-axis is frequency, mimetizing frequency, is a splitting on the energy level that should be just a Gaussian around the zero energy. And this splitting happens because of the correlated states. So there is a kind of a self-energy, splitting energy there, which does not happen at finite doping. Another thing that they also measure related to these flat bands is that close to zero bias, there is a break on the periodicity of electron concentration in the system, such that the density of states maps show this kind of square root of 3 by square root of 3 patterns, while as the system is doped away from the region where the flat band has its main density of states, the pattern comes back to be something similar to graphite or graphene. So let's start the investigation on the effects of this flat band on the electron-electron interactions in the system. So first we need to model these surface states. So if one takes a bulk system with kx, ky, and kz momentum as quantum numbers, the momentum topology is just a torus, right? Because of periodic boundary conditions. The strategy here then is to make a cut in the torus by introducing an impurity wall, and then looking at the states at the edge of this impurity wall. And we can do that using Green's functions formalism. In this way, we mimetize the experiment of STM, which can only measure a few layers from the top inside the material. So what you're seeing here is the spectral function. So basically the probability of finding an electron as a function of momentum kx and ky. And what you see is exactly the flat band at charge neutrality at the k and k prime points. And then away from the from charge neutrality, there is only a metallic dispersion. Now, the way of studying the magnetism in the system is computing the magnetic susceptibility. So to do that, we need to do a contraction between Green's functions. So here we need to take into account the integration of momentum and Matsubara frequencies, which is not computationally easy. So that's the first challenge, and the need for very low temperatures. And then we solve this problem computationally, and then add the Hubbard U as the interactions between electrons. And then we're going to see which are the main effects of this Hubbard U when the flat band is there. The spin susceptibility in the interacting case is treated using the so-called random phase approximation, which makes the susceptibility having this phase where the US matrix is related to the Hubbard U. And finally, from the generalized Stoner criterion, we get the kind of magnetism, and exactly for each values of U, there is the onset of antiferromagnetism, ferromagnetism, ferrimagnetism, and etc. So let's start this analysis. So we first compute this susceptibility, and we get two sharp peaks around the K and gamma points. So what you see in the x-axis is the scattering momentum. So a sharp peak around the gamma point is actually pointing out to scattering vectors intra-valley, inside the same pocket, while a sharp peak around the K point is inter-valley. And they are also related to different magnetic patterns, which I'm showing here. So the colors mean something. Red is up, pointing up, and blue is pointing down. And the radius of the circles is the intensity of the spin density. So what we see is that related to the intra-valley scattering, there is the usual graphene unit cell in the magnetic case, while related to the inter-valley scattering, there is that kind of square root of 3 by square root of 3 pattern as seen in experiments. But now we want to understand something more, which is the effect of the Hubbard U. So first we notice that the split in the density of states is related to the appearance of a self-energy. But the self-energy of a magnetic system or a system displaying a spin density wave is related to the susceptibility. It is actually given by the complex plane integral of the susceptibility and also the normal state Green's functions. So every pole of the susceptibility will give a certain frequency where the self-energy is non-zero, and then there is this kind of splitting. So we now investigate the poles of the susceptibility. And what we see is actually that there are two regions here. So in the y-axis, that's the imaginary frequency with the poles, and the x-axis is the value of the Hubbard U. And the colors as brighter is larger, the value of the imaginary part of the susceptibility. So what you see here are the resonances of the susceptibility related to the poles and therefore the self-energy. So there is an entire region which is just a continuum contribution of several different electron-electron interactions from different kind of scattering momentum. But then at low energy, there is this surface contribution. And what we see is that the Hubbard U actually in principle starts to suppress this first resonance here, meaning that the low energy self-energy is going to zero as the Hubbard U, the electron-electron interactions are turned on. And that's really odd, because usually with the Stoner criterion, this should only go up. And I'm going to show examples where that happens. So our next step is to investigate why that happens and what happens at higher values of Hubbard U. So increasing the Hubbard U, we actually see something. So the following thing. So I'm showing to you now the inverse susceptibility in maps, zooming in around the gamma and K points, which are these peaks, exactly at charge neutrality where the flat band is. So exactly at 0, you see the sharp peak. So the value 0 means a divergence of the susceptibility. So white is where we are looking at. So at 0 Hubbard U, this peak is exactly at the high symmetry points, gamma and K. However, as the Hubbard U is increased, and we see that that actually is something that we have to take into account because it suppresses a state. Now there is a continuum of divergences of the susceptibility, of the spin susceptibility. And that's actually energetically favorable, as we can see right here. So we take, for example, this case, and we zoom in and we take exactly one value of momentum and see what happens with the susceptibility. So it starts at being really, really small, and then at a certain critical Hubbard U, it diverges. And then this divergence produces a resonance that never closes as U increases. So this is robust against electron-electron interactions. That means that the system is actually suppressing a state that comes from natural electron scatterings, or what we call nesting from the Fermi surface, and then proposing something else. The system is actually saying, I want this to be this multi-Q magnet. And finally, we notice that studying the phase space of the system, we see that actually this happens for only at the flat band. So in the y-axis, you're seeing the critical Hubbard U, which it would be expected for the exactly at the flat band to have a zero critical Hubbard U because of the Stoner criterion. Intuitively, the Stoner criterion gives that if the density of states diverges, then the necessary electron-electron interaction, the Hubbard U, should be any infinitesimal value to give a magnetic state. But then we show that if the Hubbard U is increased a little bit more, this state is suppressed. So actually, the stable magnetic states are these higher Hubbard U's. And actually for the system, we expect Hubbard U's around 8 or 9, such as in graphene. EV. And then as a function of electron density, an experimentally controllable parameter, we see that this scenario, this doesn't happen anymore. It only works at the flat band. And as we go to the dispersive region of the energy dispersion of the system, the usual Stoner criterion, where only the first Hubbard U plays the main role, comes back. So it looks like that this behavior favoring the multi-Q state is something characteristic of the flat band on the surface states of this system. So, in sum, using the impurity wall method to access the surface states, we probed for that the flat band drives these multi-Q magnetic states, and that they establish a competition between intra-valley and inter-valley scattering events, establishing a first competition between kings. With that, I conclude thanking the institutions that hosted me, the time to develop this work, and also the funding agencies. Thank you.
Thanks a lot for the talk. Time for questions.
Thank you very much. It's a really nice talk.
Thanks.
Your talk reminded me, I'm not sure if it's the exact physics, but it reminded me of the cone anomaly that usually takes place, the divergence of the polarizability takes place usually at 1D, not for 2D or 3D, but in your case you have a divergence even for 2D.
Yeah.
So this is fascinating. This is really nice. Did you already connect this? Because you mentioned a lot of keywords like nesting of the Fermi surface, divergence of the polarization. Did you connect this with the cone anomaly somehow?
We haven't thought about that yet, but that's interesting for us to discuss. I'd like to hear more.
Sure, we can talk later. Thank you.
More questions?
So the experiments that you showed there, they did not control the interaction in between the two donors there to make the splitting. But you show that you can actually, if you control, you can actually see like all the other parameters. How could you design a system where actually you can smoothly control in between and show that actually is the flat band that you were doing? Did you thought about that?
So, one interesting thing is that with all that, and including our formalism, we don't have to introduce by hand the intra-valley and inter-valley scattering. That's there already because of the flat band. So these several scattering events, they are taken into account at once, and they happen and are influenced by the electron-electron interaction through the Hubbard U at the same time too. So that's why there is a competition, because we don't control those individually. But actually an experimentalist could do that if they could control, for example, the Coulomb screening, because then one can control if the scattering happens between electrons far away or close to each other, and then control the momentum distribution of the interaction, and then favor, for example, intra-valley or inter-valley more than the other. And then there are several techniques to do that with few layer systems, right? So that would be an interesting experimental direction.
More? Okay, if not, we can conclude this session. So the program now continues. You can go to the 4th floor where we have a poster session and a coffee break as well. And then we will recap at 3:30 in the auditorium with other talks from the US and from here. Thanks a lot, everybody.